equal to 0 and R equal to infinite. Now, coming to the other laws which are very important in electrical engineering, those are Kirchhoff's current law as well as Kirchhoff's voltage law, in which we can call them as both as Kirchhoff's laws. Coming to Kirchhoff's current law, it states that the algebraic sum of the currents meeting at a junction in a circuit is 0. And if I have k number of branches meeting at a junction, or it also called as at a node, then this is the representation. Now, KCL can be stated in a different way, like sum of currents flowing from a junction is equal to the sum of current flowing towards it. So this is the representation. So this is the node where some currents are entering and some currents are leaving. So if I consider the entering currents, or sum of the algebraic sum of the entering currents is equal to the algebraic sum of the leaving currents. So if I brought them all, then I can say that the value will be like this. So which nothing but the algebraic sum of the currents meeting at a junction is equal to 0. Next, coming to the Kirchhoff's voltage law. So in voltage law, it states that at any instant, the algebraic sum of the voltage around the closed loop or the circuit is 0. For a closed loop having k elements, then the relation you can represent is like this. So this is the circuit where you have battery connected, which is a source, or the active elements. These are the three resistors which are connected and they formed a closed path. And then if I apply KVL, then I can write the equation as like this. This is the source voltage Vs minus V1, V2, V3. So where you can represent the supplied voltage or the active element supplied voltage is equal to the passive element observed voltage. Now coming to, if I consider all the elements which are connected like this, this is series combination. We can call them as series combination of resistances. So if the resistance are connected in this way, each and every resistor will have voltage across it. There is a drop across the resistor. The voltage across each and every resistor, you can represent R1 will have the V1, R2 V2 and R3 V3. Then according to KVL, I can write down V equal to V1 plus V2 plus V3, in which if I consider voltage current relationship, where V is, by using Ohm's law, I can write down IR1, IR2 and that, from which I can write down that the relation as I equal to Rs, where Rs equal to R1 plus R2 plus R3. So from this I can say that the number of resistors connected in series equal to the sum of individual resistances. For n series resistance, we can write down this as from 1 to n Rj. So all the equal resistances. Now, likewise, if I connect all the inductances L1, L2, L3 up to Ln in series, then the equivalent inductance will be L equivalent equal to sum of all the individual inductances of the inductors. Then, if I consider the capacitors are connected in series, then the equivalent capacitance will be different. This is what. So this is the 1 by C1 plus 1 by C2 up to 1 by Cn. This is the if capacitors are connected in series. Now if I consider the parallel combination of resistances, this is the parallel combination of resistance. Again, if I consider three resistance, then they'll have three branches. Three branches will have the three resistance, three currents, individual currents I1, I2, I3, and the total current entering these three elements is I. Then I can say that I equal to, according to KCL, I can write down that the entering current, if I consider this as a node, the entering current I equal to leaving currents I1, I2, I3. So then, if I represent entry current equal to leaving currents, according to KCL, I can replace with I in terms of the voltage and resistance. Then I can write down this equation as 1 by R1 plus 1 by R2, 1 by R3 are the equivalent resistance value with V. Then I can write down this as the I equal to then I equal to V by Rp, which is here Rp is parallel resistance value. So in which parallel resistance is 1 by Rp equal to inverse of 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. So which is the reciprocal. Reciprocal of equivalent resistance of number of resistors which are connected in parallel equal to the sum of the reciprocals of the individual resistances. Then you can write the relation as like this. Now coming to the, if the inductances are connected again in parallel, then the equivalent inductance will be reciprocal of the equivalent will be individual reciprocal summation. This the one. Now in case of capacitance, that property is changed. If the capacitance are connected in parallel, then the equivalent resistance will be like this.